In this video, you will learn how to perform a simplified design of a PV system. A simplified design of a PV system can be performed as a first step to check the viability of the design for a particular location. This type of design is aimed to quickly calculating the PV system requirements based on the customer's needs and input. There are two design strategies that can be used to carry out a simple PV system design. These strategies can be applied to both grid-connected and standalone PV systems. The first design strategy is used when only the bare minimum input requirements are known, such as PV module type and the loads used in the PV system. Consequently, this strategy produces a very rough estimation of the PV system design. The second strategy is a bit closer to reality, since it includes additional details such as charge controller type, inverter type, and the maximum power point tracker. For both these simplified strategies, many oversimplifications are applied. These include the use of a simplified load profile and disregarding the location meteorological effects like ambient temperatures and the wind speed. Moreover, for the simplified design, we simply use the standard test condition data of the PV modules, and therefore we do not take into account the sun position or PV module orientation. In this video, you are going to learn about the different steps involved in the first design strategy. The second simplified design strategy will be discussed in the next video. Let's begin with the first strategy. This method follows a 6-step plan to complete a PV system design. We will use a standalone PV system for our explanation. The first step involves listing all the loads in a so-called load table to determine the daily load demand in ampere hours. A load table basically contains information about the loads that will be connected to the PV system. By filling out details such as device type, its rated power, and its average daily operational time, the energy requirements of the loads can be calculated. As you may notice, we have used separated load tables for DC and AC devices. The total energy requirement of the respective loads are calculated by multiplying the power rating of the load with its average daily operational time. In the case of AC loads, there is an additional step necessary to convert the AC energy in terms of its equivalent DC energy. This is done by dividing the AC energy usage by the conversion efficiency of the inverter. In this simplified design, we assume this conversion efficiency to be a constant value of 90% for a good inverter. Once the total energy of the loads are obtained, we must decide on the nominal system voltage of the PV system. This is usually either 12, 24 or 48 volts. Then, the daily total ampere hour requirement of the load is calculated by dividing the total energy of the loads by the nominal system voltage. An overview of this step is shown here. Please note that a PDF version of all the design steps of both simplified strategies will be made available to the students for their reference. Now, let's move on the next step, where we determine the battery and the system losses. System losses include energy loss in the cables and the other components. For this simplified design, the battery and the system losses combined can be assumed to be equal to 10%, which means they operate at a 90% efficiency. The final daily load demand of the system is calculated in ampere hours by dividing the value obtained in step 1 by 90%. So now we know our load demand. The next step is to design a PV array such that its power output can meet the load demand. This starts by obtaining the equivalent sun hours, ESH, for the PV system's location. The equivalent sun hours is an important parameter when carrying out the simple design of the PV system. An equivalent sun hour, as you may recall, is defined as the number of hours per day that a certain location receives one sun illumination averaged over an entire year. We can gather from this figure, for example, that a horizontally inclined panel in the Netherlands receives approximately 2.7 ESH per day. Once the number of ESH is obtained, we can determine the total required output current of the PV system array. The output current is obtained by dividing the daily total ampere hour requirement, determined in step 2, by obtained equivalent sun hour value. In step 5, the PV system is sized by determining the required total number of modules. To find the size of the PV array, we first determine the number of modules connected in parallel. This is achieved by dividing the PV array current, determined in step 4, with the PV module's maximum power point current, found in the modules datasheet. Similarly, the number of modules to be connected in series is obtained by dividing the nominal system voltage, chosen in step 1, by the PV module's maximum power point voltage, which is also found in the module's datasheet. The total number of required modules is determined by multiplying the number of connected modules in parallel with the number of connected modules in series. In the sixth and final step, we look at the battery requirements of the system. The batteries should supply power when the load demand exceeds the power generation by the PV modules. The first step is therefore to decide how many days of reserve the batteries should be able to supply power. Generally, the number of reserve days can be chosen based on the type of loads considered in the PV system. For telecommunication systems, for example, the number of reserve days could be about 10 days or more due to their criticality, while for residential systems, the number of reserve days could be 5 or even less. Once an appropriate number of reserve days is chosen, it is multiplied by the daily ampere hours requirement of the system, determined in step 2. The resulting value divided by the battery capacity value gives the final minimum battery capacity needed for the PV system. For the simplified design, a battery capacity value of around 80% can be chosen as a safety limit to prolong the battery life. With this final step, we have now completed the simple design of a PV system. Up to this point, we followed the various steps to carry out a standalone PV system design. The same design strategy can also be used to carry out a grid-connected PV system design by omitting the battery calculations from the steps. The battery losses in step 2 and battery requirements in step 6 are therefore omitted, while the rest of the simplified design steps remains the same. This concludes our discussion of the first strategy to perform a simple PV system design. In this video, we learned the different steps to complete the simplified design of both grid-connected and standalone PV systems. In the next video, you will learn about the second simplified design strategy.